Without taking much of everyone's time, let us start the program. Let me introduce our today's keynote speaker, Mr. Atul Bhobe. He completed his bachelor's from Mumbai University in 1985 and MSc Civil from Ann Arbor, Michigan in 1986. Mr. Atul Bhobe is second generation structural engineer and presently managing director of TPF Engineering Private Limited, and he is on the board of directors of TPF Group, an international multidisciplinary consultancy company with over 4,500 persons operating in 65 countries. He is life member of various professional society bodies. He has experience over 33 years in the field of structural consultancy in general and bridge engineering and infrastructure in principle. He is well recognized and popular speaker of various forums. He published and presented over 150 papers in national and international seminars. He won several awards on bridges and structures designed and engineered over the last 3.5 decades. Please welcome on the stage Mr. Atul Bhobe with great round of applause. I request Aarti to present a token of love from Epicons.
So good morning, ladies and gentlemen. It's a pleasure and privilege to be delivering a keynote for workshop 79 organized by Epicons. And as requested by Mr. Jayant Kulkarni, I will declare this workshop formally inaugurated. In addition, before I start delivering my lecture, although Hitali has already mentioned that Epicons has won the award, I will like to personally congratulate Jayant Kulkarni and his entire team on winning a prestigious Industry Excellence Award from Institution of Engineers. It's not a small thing to do that. Also carrying out 79 workshops in this era of skill development that the government is focused on, and a lot of engineering skill that needs to be enhanced in the industry. I think it's a great effort on the part of the private sector, especially Jayant Kulkarni and his team need to be complimented for holding these seminars. So without further ado, I start with my lecture. And what this lecture is going to be is, for those of you who have attended, because I think this is called part 2, so those of you who attended part 1 would have heard me present the past of structural integrity management, as I like to call it, SIM, as I like to call it, instead of IBMS. In fact, when I delivered that lecture, I called it IBMS, the Integrated Bridge Management System that's being developed by the Ministry of Road Transport and Highways. So the presentation that I made last time was talking about the kind of problems that we had in IBMS. And I stopped after telling you what the problems were. I did not tell you what the solutions were because of two things. One, it would have taken the whole day. And two, that particular seminar was more focused on the experiences that we've had while implementing the IBMS, because that lecture was then followed by the lecture of Sachin Joshi, who talked about what IBMS is and so on and so forth. This part of the presentation is going to talk about the future of structural integrity management for bridges and structures. This is what is going to be in the future. This is not something that we've already done. This is not something that we already have experience with. But when I present this, you will realize that each one of you almost has had all the experience in the world. It's just that we have not been using it. So the overview of my presentation is the why, what, and how of structural integrity management. So let's talk about, to begin with, the why. And the three most key points that I made in the last presentation about the experience that we already had in the IBMS was the problems of the human interface with the data and the integrity and trustworthiness of such data. What do I mean by this? This is a very abstract statement. It's almost like coming from a digital industry kind of a statement. When we actually inspect bridges or structures for that matter, the biggest problem is in identifying what constitutes a crack. I'm telling you a very rudimentary, very basic thing. When you do the first reconnaissance survey, or the first recce as we call it, what we try and see in a structure is to see if we can find obvious wear and tear, which is manifested by cracks in concrete. In steel, it's even more difficult because you can identify only corrosion and rust. Very few people will understand on visual inspection the difference between rust and corrosion. It's very, very difficult to identify which is what stops at rust and what becomes corrosion. So there is a problem of the human interface and brain assimilating that data and converting it to a conclusion. And such data, therefore, the integrity of such data, therefore, and the trustworthiness of this data becomes doubtful. What we also do not do, and I mentioned this in my last presentation, is that we do not do a balanced life assessment of those structures. And it's at this given time, with the data that we collect, it's practically impossible with the model that we are using to collect that data, because we don't actually collect the data with the basis and thought of calculating balanced life. To my mind, balanced life calculation should be the first and the primary goal of inspection of the structure, because what you are interested in at the end of the day is what's the service life assessment of the structure and what's remaining in that structure. Until the analysis and conclusion modules are added to the current monitoring that we do, what we are doing has limited value. Now, this is a very obvious statement, and I hope you appreciate what I'm trying to say here is that we spend a lot of money, time, and effort in trying to get to reality. Corrosion in steel, corrosion in reinforced concrete, cracking in reinforced concrete, cracking in pre-stressed concrete is reality. But what we actually investigate after that reality is fiction. Because what you are doing in trying to evaluate fiction is trying to establish the extent of corrosion, the extent of damage to the structure. But we don't realize that what we actually want to know is what's the balance life of the structure. If somebody goes to a hospital and is detected with cancer, the first question is what stage of cancer is the person in and what's the status of his remaining life. How long is he going to live? That's the most obvious question that comes to one's mind. As engineers, unfortunately, we are not able to answer such questions at this given moment because of the limitations of our minds and because of the way in which we think. The way we inspect structures is we go with a preconceived notion in most cases to understand and appreciate the damage and try and mitigate the damage so that the structure lives for 1 year, 3 year, 5 year, 10 years, whatever. We don't really do a service life assessment and a balanced life assessment of that structure. So here we have redundancy of data. What we are collecting, there is a human mental bias, like I mentioned, in everything that we do and everything that we collect. After we do that collection, the reaction time that you have is practically zero, which means that the moment you see a crack and to the time that your mind starts thinking that there is a problem in this bridge, there are a very, very few engineers who can actually say, just like the Nadi doctors we used to have, who used to check your pulse and say that, okay, you probably got a heart disease or you've probably got sugar or whatever. There are very few engineers who can look at a structure and say that this is the problem. Most engineers will react and create a panic situation, which means that, which is what you're probably seeing on ground when the Mumbai Municipal Corporation is closing down 35 bridges overnight. Probably 3, 5, 10, 20 of those bridges are really in a panic situation, but not all of them can be in the same situation one fine day. That's not possible, right? That's the most obvious logical thinking mind solution to a problem. And like I said, it leads to panic situation. obviously leading to wrong decision making, which means you close down the structure, you close down the bridges, you evacuate dilapidated buildings, you stop production in an industrial structure, just because one human mind decided that the structure is dilapidated, without any basis of balanced life. It obviously skews budgets, and it's not helping with forecasting, because we are not forecasting anything at this moment. We are not drawing conclusions from all the data that we have, and we are definitely not creating budgets and forecasting based on that data, because that data is inadequate to do that. Now, what do we need for balanced life assessment? There's inadequate data on locations. In most cases, what do I mean by this? It means that when you see a crack, most people come up with the notion that the structure is dilapidated, it's got a problem, there's corrosion, there's too much of cracking, etc., etc., etc. And in that anxiety to report cracks, a lot of times the precise location of those cracks is lost. By the time a report is made, by the time a report is generated, by the time it goes to the decision-making body, a decision is taken and you go back to inspect the structure, the crack has already moved. You already have one crack at quarter span, and then now the next time you go 3 months later, you have 20 cracks at different locations, and you've lost the importance of that data. A lot of times, the location data is incorrect. I've seen bridges inspected in wrong spans because the number of the span mentioned was incorrect, and a lot of time and effort has to be spent. And the same thing happens in buildings. Span number 3 has a problem. Nobody tells you whether it's span number 3 from the left bank or the right bank. So you go and inspect the span number 3, and a lot of times you find there's nothing wrong with that span. You come back, report to the client saying that the span is perfectly hale and hearty, and lo and behold, you get photographs saying that this is the cracks, your inspection is faulty, you have not done this, you have not done that, and so on. Modern techniques capable of identification are not yet available to yield perfect results. We have the LIDAR, which is a modern technique, but even that is not yet able to yield perfect results. It's still in the experimental stage as far as balanced life assessment is concerned. And the biggest problem is, and I always say this, is the biggest problem that we have is our extreme belief in Newton. I don't know how many of you remember Newton's first law. A body at rest does not move until acted upon by an external unbalanced force, inertia. Inertia in society is what prevents us from taking decisions that we would have otherwise taken. Resistance to change. And I've said here on account of service providers, and here almost everybody is a service provider, because what we are doing at some point in time, even the consulting engineer is a service provider to the owner. The owner is a service provider to the society, and the contractor is anyway a service provider to the owner. So at different roles that you play as service providers, there's resistance to change at every level. The analysis and conclusion module, which I talk about, like I said, we don't have these modules at this moment, and here I'm talking about IBMS specifically. What we have in IBMS at this moment is a lot of data. We don't know what to do with that data. We have the location of the structure, we have the general arrangement drawing of the structure, we have a condition survey, the first visual condition survey of the structure, we have the first NDTs done on few of those structures where mental capability decided that those structures have a problem. So we have this data already, and that's generated over the last, let's say, 3 years. We've lost 1.5 years due to inertia. After that program was suddenly suspended. So we've lost 1.5 years after that. We haven't generated data after that. But even in those 6 or 7 years that we have worked with IBMS, we still don't have a query module on that software, which means that I know that I have the data, but I cannot query it. So I know that I have 175,000 bridges on the national highway network. I know that we have an equal number on the state highways, an equal number on the urban local bodies, and probably an equal number on the metros. So you're close, the country has close to 700,000, maybe even more number of bridges, just number of bridges. And unfortunately, all I know about these is that 1/4 of these bridges, I know where they are located. I know what spans they have. I know in general that some of these bridges have a problem. I know that NDT has been carried out. And what do I do with all this knowledge? Nothing, because I cannot query it, I cannot conclude anything from it, and I cannot move forward from it. Decision-making dashboards are needed, and they are missing in this whole exercise. Budgeting and forecasting needs to be made available so that the decision-making body is helped with all this data. Otherwise, all this data is useless. And most importantly, the last point, balanced life assessment needs to be defined. We don't have a definition of balanced life assessment at this moment because we simply don't do balanced life assessments. It leads to a solution which is not perfectly designed as per prescribed standards. The standard that we have for bridge management systems was written way back in 91, 92. And that already has, and when I say standards, the Indian Road Congress Code and a special publication both. And what we have in that is it tells you what query and conclusion model is needed. But we haven't done that yet. We have stopped at maybe after about 20-25% of the work has been done, we have stopped at that. So we have looked at the why. Why do we need to do what we have to do? What could we do? Well, for one, we could use structural integrity monitoring software. It's state of the art. There's no human interface needed, and it is scalable. Now, what do I mean by this? I'm going to show you in the next couple of slides, the second part of my presentation, what a structural integrity monitoring software does. But before I start talking about structural integrity monitoring software, you need to know in principle, what I'm talking about. Imagine a scenario where you could be monitoring every bridge that I just talked about, 700,000 or 800,000 bridges. You could monitor each and every span of each and every bridge sitting right here. That's what we are looking for. How could we do that? For that, we need state-of-the-art software, of course, because it's all digital. We need to reduce human interface. And of course, it has to be scalable. So all the three attributes that I mentioned need to be there in this system. What does this mean in simple terms? Imagine that you could see on this screen a simple dashboard, just like you see in those traffic data centers. You see all the traffic moving, you see the traffic lights, you see where the problem is, you see where the clog is, and you can remove bottlenecks. You can have a dashboard which is telling you which particular span of which particular bridge is undergoing what stress at any given point in time. Now, why was all this not possible all these years? Why could we not do this all these years? What I'm saying is very, very easy to do. You just put CCTV cameras and do this. For two things. One, we did not have the technology to do it. And two, we didn't have adequate computing power to do it. For almost all structural engineers who work with software, let's say STAD, SAP, MIDAS, Sophistic, LEAP, any software that you use, it works on the principles of finite elements. And as many of you would know, if you have 1,000 million, well, not million even, 1,000 degrees of freedom to solve, then your software generally crunches through one typical span of one typical bridge. Maybe it takes you 4 hours, maybe it takes you 6, depending on the complication of your model. It might take you 4 hours, 6 hours to run through one single iteration of a finite element. Unfortunately, most civil engineering applications don't really do finite elements in the real sense of the word. What we do is what is called matchstick models. what I call matchstick models, which means if you are doing STAD, all you are doing is you are modeling the building or the bridge as matchsticks, beams, maybe if I call it that, and we stop at that. Most of the design modules of STAD, SAP, Strudel, etc. are also basing their designs and calculations on matchstick models. They're not basing them on real finite elements. What does that mean? It means if you're doing, let's say, a steel truss, and you want to know what happens to a particular bolt or a rivet at a particular joint of a truss, then the software that you currently have and the model that you have currently built cannot possibly tell you that. If you need to go to that level, you need a real finite element software. You need to be able to use the finite element capabilities of your software, which in most practicing engineers' office, you will find that that's given the go by. We don't really do finite elements to that level. Of course, we do it for, let's say, a few complicated structures. Let's say you would do it for a cable stay bridge, or you would do it for maybe a multi-span continuous truss or something like that, but not, you cannot imagine doing that for a 5 meter, 6 meter slab bridge, because you think that a slab bridge is conventional. A building which is 20-story today is passé. You would say that, okay, it's very easy to do a matchstick model and the results are okay. I don't need to do a finite elements. The reason we don't do finite elements in most cases is not because we don't want to do it, but because it would take an enormous amount of time to do it, an enormous amount of computing power to do. What I'm about to show you is the latest state-of-the-art development in computational mathematics, which allows me to solve nearly 1 million degrees of freedom continuously in less than 20 seconds. This is a software that's, well, this is one software that I'm showing you. There are several that are available. But once you have that kind of capability, imagine creating a simple model for any structure that you want. And it doesn't operate on your computer, it operates in the cloud. So it doesn't take, like you can operate it on your iPhone, you can operate it on your iPad. It doesn't need RAM or ROM on your computer. So it's on the cloud, and it does all that in the background. Okay, so this is absolutely state of the art. This is something that's so how could we do it is the next question that comes to mind. So that's the name of the software. It's called Axelos. Okay, and this is only, like I said, one of the software that's available on the market. It doesn't have to be really only this. You could find others. There's a PDF. So from simple IBMS, I'm now moving to what's called digital twins. So what this does, it creates a complete twin on your computer. At this moment, this software is being used to monitor offshore platforms. And why offshore platforms, you might ask, is because this software was originally developed in MIT by 3 PhD students. This was their PhD program, almost 15 years back. But for the first 10 years, because their research was funded by the US Department of Defense, they were obliged to use the software only for defense purposes, for strategic installations for the US Department of Defense. So for the first 10 years of its life, this software was tested on US Department of Defense installations. And some of those installations were offshore installations. So the first application of this software in the civilian industry over the last 2-3 years has been in the offshore industry. It's only the first time that we are trying to think of ways and means of using it for bridges and structures. So it's the next generation physics-based simulation. So what you see on the right is the Lockheed jet, and on the left, the simulation of the same jet. Imagine a finite element run that you would do on the same jet, and you see the finite element analysis on the left. That's an application in aerospace engineering. So as you can see, the R&D was funded by the US Department of Defense. MIT developed the technology protected by issued patents. It's got over 100 academic publications already, and it's equal to 150 years of research and development. So how can you understand how a structure will perform with particular regard to all these stresses and deflections, fatigue life, natural frequencies, mode shapes, vibration response, shock impact damage, temperature distributions, and modifications or upgrades. Now this is where I'm saying that we are moving away from the mental infringement of collection of data. You are now moving to digital collection of data. So all we need to do for this software to actually analyze all this is to attach certain attributes to the structure. Attributes in the sense a strain gauge, an accelerometer, or the like. You could attach anything that measures data of the structure. It could be brought back to the software model that we have, the digital twin that's created. And the twin, based on the data that you're collecting, will recalibrate its own model and send back to you conclusions that you can use in real time. What does that mean? Let's say this particular bridge that you see has strain gauges and deflectometers attached to mid-span, quarter-span, the cable. It's measuring all the data. The bridge already exists in my model on Axelos, on the digital twin. It's already created. It's already calibrated based on design loads. But normally design loads don't actually corroborate with the service loads, which means, let's say I designed the bridge for 70 R, but the actual load that's moving on the bridge is a 5-ton truck or a 3-ton vehicle or whatever. So what this does is, for your design loads, it's already created a benchmark of low stress and high stress, or low strain and high strain, or low deflection, high deflection, or all of these. Once you get the data in, even if there is no load on the bridge and there's data coming in, the model in the background is continuously calculating based on the data it receives. Let's say there's wind load and there's no live load. It's continuously calculating the effect on the structure and throwing back results at you continuously in real time. Now, this was not possible earlier. Imagine a bridge like that. If you were to do a finite element model in your office at this moment, it'll probably take you minimum of 10 to 12 hours just to do one run of a finite element software. Let's say a pushover analysis, or let's say a second order deflection analysis would take you 10 to 12 hours. This software is capable of doing that in microseconds. That's a big leap from the way that we are conventionally taught to think of finite elements. So imagine this being done on a real-time basis, which means that I'm getting deflection, I'm getting strain, it's calculating in the background, and on my screen, all I'm seeing is that there is a band of top strain, top stress, top deflection, bottom deflection, and I'm seeing a graph which says that I'm in the safe zone. The moment it goes either below or above my safe zone, it will press panic buttons to say that now you need to inspect the structure. And this is where something is going wrong. Because it's a finite element model, it will be able to tell you probably maybe with 10% accuracy, with 95% accuracy, 10% of the locations where this could have gone wrong. So you need to inspect only those 10% locations. You don't need to inspect the entire bridge to find out what's going wrong. That's the bottom line. Okay, all this English that I'm telling you is leading to that. So it's the fastest and the most advanced engineering simulation tech that's available currently in the market. And this is, of course, all marketing, blah, blah, blah. I'm not going to get into that. But yes, so how is this technology different from the current level of technology that civil engineers are using? Remember, I keep repeating civil engineers and structural engineers because this is not currently being used in the civil engineering industry. This is being used more in the aerospace, more in the floating offshore platforms, and so on and so forth. That's why you'll see the large boats, etc., in these models. There you'll see port structures at the bottom. That's a crane, and you can see the finite element. I don't know. Yes, the finite element modeling that has been done. This entire boat, the finite element modeling has been done, and it's, like I said, easily solvable models are with more than 100 million finite element degrees of freedom. This was unthinkable till we got a software like this. So this is parametric modeling. What does parametric modeling mean, and I talked about scalable software. What it means is that, let's say you have modeled for this particular structure a joint like this. And you come across another bridge or another structure where you have a same joint. You don't have to recreate the joint. You don't have to resolve the finite element model. It stores the joints as parameters. Now, remember the way that this is being done is completely different from the way that we do it currently. In your current models that you do in your office, if you find that in your building, your column is out by say 100 millimeters, the way that you would model is to redo the entire model, because just moving a column by 100 millimeter doesn't work. And you have to redo the entire analysis again, look at all the members again, and do everything again. That takes a lot of time. This doesn't require you to do that. For example, I go to this structure and I find that this particular beam is out of its line. I just need to change that one beam. And even as you change the beam and click solve, within seconds it tells you what's wrong with this. A normal finite element model with this kind of degrees of freedom takes hours to solve. This does it in microseconds. That's the big difference in computing power and algorithms that are cloud-based. It's got component-based modeling also, which means you can do modular design, which means you've designed a truss for one structure. You have a similar truss elsewhere. You don't need to resolve it. You just need to modify that existing structure, and it will solve that based on component-based modeling. This is what they're currently using it for. Some of the applications that I talked about, they do wind turbines. You see the stress pattern on the wind turbines. They do pressure vessels. They do rotating machinery, which means gears. They do fixed structures, which is steel structures essentially, and they do floating structures. Now, one of the most amazing applications I found, which is not related to civil engineering, they also simulate the human heart. The software simulates the heart, and you will be amazed to know what they use it for. Most of the drugs that are used need to go through a phase of what is called clinical trials, which means you try it on rats, then you try it on monkeys, then you try it on human beings. That's the series of clinical trials. But because of large issues with animal rights and things like that, there's a problem in getting rats and monkeys and making trials on them. So what they do is they have found that certain drugs give electromechanical signals to certain nerves of the heart. So they have mapped those electromechanical signals of your drug. All you need to do is come up with your drug and say that this is the electromechanical signal that I need to give the heart and see how the heart reacts. They use this software to see how the heart reacts to certain electromechanical signals. They also map the brain, and that gets scary. That's where it starts getting into domains which are scary. And they can actually control your brain with electromechanical signals. You might have seen Google with a helmet, where if you turn your head, they know which direction you're looking at, and your Google Maps actually shows you which direction you're going. So that's an application of a software like this. That's the heart of decision making is a software like this. But of course, they don't use this software for brains yet. There's another software they do that, but they're using this for hearts, and they're using it for modeling stents to see which material of stent has a longer life, fatigue life within the body, and it's really amazing. I've seen it myself, and sometimes it scares you. Substructuring or super elements also use components, but this has key differences, and this talks about what key differences we have. This is getting into more of the mathematical model approach that it has instead of the conventional approach. For some of you who might have worked with conventional civil engineering finite element software, you know that our software generally works on the basic principle of inversion of matrices. That's at the very basis. The software works on inversion of matrices. This does away with that. This is an algorithm that does away with inversion of matrices. It moves completely away to a different algorithm. And that's the reason it's faster. So it's 1,000 times faster technology. Update the model with sensor data, and predict asset performance in real time. Now that's where it gets interesting, and that's what I was talking about. Is this model that you see, that's a floating platform or the like, and you see an online stream that tells you the red areas, which are the scare areas of that particular model at that particular time. And imagine an offshore platform like that. You can't inspect that just like a building and a bridge every day. It's a much more complicated inspection regime that they go through. And I'm sure the IRS people will know more about what I'm talking here, because this is more in the shipping domain than anything else. So how are assets currently designed and managed? What will fail, fix it before it breaks. That's not how we operate at this moment. We wait till it fails and then we try to fix it. When? So repairs can be scheduled to minimize downtime and cost. What if scenarios can be run? You could model the bridge and say, what if this particular member, instead of being like this, is like that? What happens if a bolt is loose? What happens if the splice plate is not fitted properly? What happens if the weld fails, and so on? So you could do what if scenarios. Build it right, which means that if you incorporate this early enough in your project, you could actually monitor the asset as it is being built, which means that even during the construction phase of the model, you could be getting real-time data and trying to see if there's something wrong that's going on. Of course, I've already talked about this. Speed cannot do big complex assets, inaccurate, and will not do real-time in most cases. So to overcome these limitations, engineers typically use, I've already talked about this, what we do, how we do quality checks on this, etc., and then what we want to do in the future. And this is what it talks. This is in pictorial terms what I just told you. This is the parametric and material models. You could pre-analyze components and keep them ready. You could create a library of model components and keep it ready and simply plug in those components when you're creating a model. Connect components to create simulation-ready models, model the setup, solution and analysis, and then post-processing, and then go back and do the cycle again till you get a result that's absolutely perfect and matching with your structure on the ground. So that's the digital twinning that's happening. So here you see one more example of the parametric component modeling, and you see the level at which the finite elements is happening. The whole structure that you see here is actually modeled right down to this. You see the tear here that's induced. You could move this from here to there to see what happens if that tear has happened. And you could move the structure up and down to see what happens. You see the stress concentrations at locations. You could do all kinds of what-if analysis, which you're not able to do currently. So that's another model that they do. That they, like I said, they monitor offshore platforms, floating platforms. That's one of the large platforms that they're monitoring. That's the degree of freedoms. It's unheard of, 100 million degrees of freedom. We don't normally do that currently on civil engineering structures. Again, you see the level of detail on the structure. You can see the finite elements that's done. So you can from this, you can go to that, from that to this, and down to the exact bolt and nut. You can actually check each and every component of your structure. So you can induce cracks. You can check what happens if a crack were to happen on a hull of a ship, and you could see where the stress concentrations are, and so on. So I can keep talking about what they do also in different kinds of models, but these are mostly, like I said, not in the civil engineering domain. Well, okay, here's the offshore platform modeling, and you can see day 1, day 4, day 10, the sensor data displacements. You can see the actual data that they have. I've seen them get data from the wave patterns, from the wind pressures. They measure the wind, they measure the waves, direction of the waves, the high tide levels, the low tide levels, everything. Practically everything is monitored. So here you have the calculation of the fatigue damage. So that's more now getting into balance life of the structure. So you can actually calculate what the fatigue damage is. In the past, see, this is what the fatigue damage would have been Okay, this is what it actually is. So there's an extension of service life of the structure. That's the extension to the service life. That's the calculation for service life. We are now getting into assessment of balanced service lives. So this is the future of even this software. I'm already calling Axelos the future, but this is the future of this software. It's now being connected to artificial intelligence and machine learning, which means that if I have a truss bridge and I have enough data generated over, let's say, 1 year or 2 years, and I've connected that to the conclusion and query model, which tells me what was going wrong when this particular stress level exceeded on that bridge. It will start learning from the answers that I'm giving it, and the next time that happens, it will tell you that this is what has gone wrong. So you don't need to tell that story again. So it's got predictive life assessment and predictive failure models built into it. This development is going on at this moment, even as we speak, and it is expected that by fall next year, which means about August or September, around the same time this year, Axelos will introduce machine learning and artificial intelligence into the game, which means that the first problem that I mentioned, the human data extraction limitation, will be overcome. You will not need a human interface to actually go and physically inspect anything until the model tells you that there is something really going wrong. You need to inspect the bridge, and then you could go and inspect a specific span or a specific area of a particular bridge. Even today, when we do, let's say, a structural audit or we do inspections of bridges, it's impossible physically to inspect every square millimeter of the structure. It's practically impossible. So we are getting there slowly. So the potential extension to structural health monitoring, I already mentioned this. So in summary, it's large-scale models, hundreds of millions degrees of freedoms. Step change in performance is almost 1,000 times faster than the current FEA that we do. It's parametric, it's sensor connected and controlled, both. And you do structural health monitoring online. So this, ladies and gentlemen, is the future of structural integrity monitoring and management as I see it. Software like this, and this is just one particular software. I have seen at least 3 or 4 like these, but each one has its own pluses and minuses. You could weigh the options before you take a call on what's best for your structure. But this is just one I thought, which I've seen very closely. In fact, we are one of the contributors to the reinforced concrete, pre-stressed concrete and steel bridges module of the artificial intelligence and machine learning that will be introduced next year. So we are contributing towards making that a foolproof software. So next year, hopefully, when Axelos introduces this particular module, it will shortcut a lot of those problems that I mentioned. The flip side of this is that, unfortunately, it will also replace a large number of engineers who are going down to the inspection level and coming back with data. But again, that's inevitable given the pace at which technology is moving. It's inevitable that some cadre of engineers will lose jobs. Because engineering, unfortunately, is the easiest profession to replace with a computer. Because engineers are taught and learn to think analytically and conclude based on analysis. Unfortunately, a computer does exactly that. It cannot replace a painter, for example, but it can definitely replace an engineer. And so from that point of view, I think what Epicons is doing in training and reskilling engineers for what's going to come in the future is a great effort. So ladies and gentlemen, thank you very much for your patient hearing. Thank you.
Friends, if you have any question, you can ask him right now, because he has come all the way, I think, from UK. He landed at 2 o'clock and he came here before we came, and he'll be leaving now. So if you have got 1 or 2 questions, at least 2 questions you can ask.
So either I made a perfect presentation or nobody understood what I said.
Can we Because you know there is a huge lot of.
For existing bridges, the problem is, well, as I see it, like I said, it's not been done anywhere. But the applications that you see are being done on existing structures, not on new structures. But applying it to concrete is more difficult than applying it to steel. Because steel at the end of the day is linear, more or less. It's linear until it goes into the failure mode. Concrete, unfortunately, is not so linear. Concrete is a non-linear material. So I would think that applying it in toto to existing bridges in concrete to do predictive failure modeling is difficult. But to get data and to analyze, concrete and steel is the same. I mean, for the computer, it's a model. So it will tell you when stress levels exceed, it will tell you when stress levels are low, etc., etc. But it probably cannot tell you very accurately the balance life or the predictive failure modeling, which it can do in steel. It can do very, very accurately in steel. In concrete, if there's an existing bridge, first, in most of our bridges, unfortunately, we don't have data. We don't know where the reinforcement is, how much reinforcement you have put, whether there's corrosion on the reinforcement or not, what's the extent. We don't have those kind of information yet. So until you have information, it's difficult to, like I said, you know, the basic, you will get it right, which means you have a 10-meter span bridge, we fit accelerometers, we take the data, and we can accurately say that, yes, there's a 10-ton load passing, the deflection is more than it should, what should be. That, of course, we can say with conclusive evidence. But to say from that okay, there, you know, this is where there will be a problem, or this is where you should go and inspect. Until there's more data, I would not say conclusively that you can do it. There is no software like that at this moment. But this, when, like I said, in the next fall, when we have the other modules in, it will start getting there, even on existing bridges.
Movements and everything. Probably you will have to install something like a total station or some device, something which will eventually get connected to a GPS device, and through a software in the cloud computing thing, it will give data. I think one of the big challenges is the security of these equipments in a place like Mumbai, because eventually someone steals these things out. I think,
so let me tell you that we don't install prisms. We don't want a total station reading.
Yeah.
We can install accelerometers. The accelerometers come in a complete vandal-proof box. You cannot vandalize it. It's fitted on the structure. And strain gauges are so small that you will not see them. Yeah. So strain gauges is not a problem. But these strain gauges that I'm talking about are absolutely 4th or 5th generation strain gauges. They have an IP built in, and they transmit data automatically. You don't need to do anything. It's got an online battery. And at the end of its life, which is, say, 10 years, you need to replace the strain gauge. That's it. Other than that, there's not the extension to this is when we will start to monitor the load that's passing on the bridge, because our biggest problem is actually not the strains and stresses or the construction deficiencies. The biggest problem is overloading, which everybody wants to close their eyes to. So if you actually do an axle load survey on most of our roads, you will find that there's an overloading to a tune of 20% or 25%. Now, until you arrest that overloading, there's not much you can do with all this data. Illegalities cannot, you know, somebody puts a bomb on the bridge, what will you do with this data? The bridge is going to blow. So, most of the other equipment is fairly vandal-proof.
When I was just going to the website of Mageba
Yes.
is one of the people who
Yes. Yes. But Magiba doesn't do what I'm talking about. Magiba, etc., will monitor bearings and connect it to stress and strains on the span, which is, I think, at least 20 steps behind what I am talking about.
Thank you.
So this is only for the structural bridges. This is only for the structural bridges. What about the others?
It's for all bridges. If it's a new bridge, it's for all bridges. Because for a new bridge, I can create the digital twin with the exact reinforcement that you give me. But for an existing RCC bridge, unless you tell me what is the reinforcement, it's a block of concrete. How do you analyze? So for a new bridge, it could be the whole spectrum.
Is this only the last bridge?
Hello, sir. I'm Computational Mathematics, CEO of Infrastructure Risk Management. Actually, a couple of days back, we spoke about 120-year durability design. So you can apply for your bridge, as I said, as a continuation of that. Can we have something like can we have something which will trigger the deterioration of it? There is nothing that is going to existing bridges are coming deterioration. Can we have something to monitor such kind of deterioration for bridges and integrate to the platform decision platform?
So okay, so answer your question. This is actually even before you start monitoring the deterioration. What I'm talking about is creating a digital twin even now. Okay, that's number one. Number two, for existing bridges where you have already identified, let's say, deterioration, there's not really much that this particular software could do. Of course, there are other methods of looking at deterioration, etc., etc., etc. But what we are trying to say here with this particular software is that we are in the predictive failure modeling rather than trying to fix it after it has happened. We are wanting to tell you that something is going to happen. We are not interested to say that it already happened, now what do I do? If it's already happened, we already have a huge array of experts who can probably do something. Of course, this software will start getting into that after we have enough intelligence built in the software. We'll probably get into that mode where we can say with conclusive evidence that yes, something has gone wrong in this bridge because the stress level appears to be more, and it's probably at this particular location that this has happened. But this could be predicted only if I'm able to create a real twin. If you don't know the reinforcement, if you don't know anything in that bridge, it's more difficult. Also, the last point about 120 years service life. Now that's, to my mind, that's all false. There's no such thing as 120 years service life. Okay, you only talk about it in a code. Because most of our codes and most of the knowledge that we currently have is based on material science, which is linked to 2 million cycles of fatigue. Most of our material stresses, most of the material values that we consider in our codes comes from the fact that we do a 2 million cycle fatigue test or a fatigue value, and then we assume a certain stress based on that value to be the representative stress in that material. Most of our bridges, or most of our structures for that matter, are so abused that 2 million cycle limit, instead of taking 120 years, is taking 20 years. So when you design that structure, let's imagine Tilak Bridge, for example. It's in the heart of the city. It was built probably 140 years ago. But for the first 80 years of its life, the Industrial Revolution created the motor car only in 1920, 1930. The bridge was built for horse-drawn carriages probably in early 1900 or maybe late 1800, 1880, 1890, when the first railway ran. So for the first 60 or 70 years of its life, it has not seen maybe even 10,000 cycles of fatigue. But what has happened in the last 20 years, it has seen instead of 2 million, maybe 20 million cycles of fatigue, and now things are falling off. But that's obvious. I mean, it doesn't take 120 years service life. That service life of that bridge is now 150 years, and the balance life is probably negative now. So I think it's in the way that we write the codes that needs to change. There was one more question, just last one. Somebody asked half a question and then stopped.
Is this open source software?
No. No, it's patented. I showed you in the first slide. It's a patented software. It will be open source after maybe another 10 years, but at this moment, it's a patented software.
I just want to ask one question about whether this technology can be utilized for the board gate structures.
Yes.
Because there my
Yes.
challenges are different.
It can be.
More than vertical load, I am pressing with the horizontal.
Yes,
load.
correct. So, like I showed you, offshore platforms are already being applied.
Because loads, if at all I consider loads, at least 120 different combinations.
Correct.
Consider for a small berthing of each shape.
Correct. Absolutely right. So you can use this for all the.
Dynamically used. Right?
Yes. It can be. If you are.
For that will be a different instrument or what are
It depends on what it depends on what kind of inputs you want to give to the digital twin. Let's say you want to give inputs of wave data, the angle at which the wave is coming, the height of the wave, the velocity of the wave, etc., etc. So there is data available like that. For most of these platforms that you saw, all the data for the last 20 years is available. So what they've done in most of these is that they've created finite element models, the twins. They have tested it for these 20-year data to actually determine what's the balance life of the structure.
We can more executive what questions aimed out in the pose. It's like my structure is designed for 20,000 DWT vessels. And if 70,000 DWT vessel comes, my management want that to be burned.
Correct.
And then that is my great challenge because there are various simulations available need to be done.
Right.
For allowing that ship to get burned.
Correct.
So that kind of simulation, can it be dynamically done? So
Yes.
that I can take a quick decision whether to accept a ship or not.
Yes, you can do that dynamically. Yes.
I think this is the only question in the session. And she will request all the further speakers to reduce the lecture by 5 minutes because we are started half an hour. Thank you, sir.
Thank you, sir, for sharing such a detailed information on structural integrity management and updating us on the advanced software for bridge monitoring.